Yeah, so good afternoon, everybody. This is Amit. I work with the Power Firmware team in Bangalore. And this is like going to be an overview of what the self-boot engine does in Power9. Kind of high-level overview of the hardware and the firmware architecture. And what are the high-level use cases kind of it supports in the system. A little bit of history over here is like in Power 8 was the first generation of power chips that introduced the self-boot engine. It was not a standard microprocessor, and it did something really less. Like it basically just enabled host boot, and that was all it did. But starting Power9, I think there have been major enhancements in the SBE, and I think going forward in Power10, we will see more enhancements in the SBE too. So I think I'll get started probably. And so what is the SBE? So it's basically a self-boot engine. Initially, before Power 8, the entire boot firmware to power up the chip and get the hypervisor loaded was done on the service processor, which kind of sat off chip and which had to connect to the main chip via the FSI bus. And going as a baby step in the OpenPOWER, I can say strategy, we wanted to abstract the BMC from the nitty-gritties of the hardware. So that's when the self-boot engine was first, like, I think pioneered in Power 8 as a baby step, and then Power 9 really took off. It's a PPE42 based 32-bit microprocessor. So what PPE stands for is basically, I have a glossary chart at the end of the deck, which I won't go through, but it's basically Power ISA Lite processing engine, model 42 of the hardware. So it's a 32-bit embedded processor, and basically it's implementing an extended subset of the Power ISA version 2.707 here. Because it's an extension, it's not directly compatible to the ISA, and the compiler has slight extensions there. So what it does beyond the normal ISA for Power is basically it does atomic loads and stores of 64-bit data, which were not supported by default. And it has about 16 32-bit programmable GPRs, visible GPRs, and I think about 18 32-bit SPRs there. There is a version of the compiler out there on GitHub. It's basically GCC 4.9.2 based one, so you would see it if you Google it. So that's the core microprocessor that constitutes the SBE, but that's not all. There is a dedicated 96 kilobyte of SRAM, which is the primary and the fastest way that SBE can execute instructions. It has customized peripherals around it to do specific functions, and in general, we call them bolt-ons. The next charts, I'll go into details of what those bolt-ons are, and the associated firmware that actually runs on the SBE hardware itself. So it's a term that's interchangeably used in hardware and firmware. Like this whole block of hardware along with the firmware running is called the self-boot engine. Where does it sit and how many instances we have per chip? So every Power9 chip has one instance of the self-boot engine. So Nimbus and Cumulus, both of them support the self-boot engine. The recently announced latest variants of the Power9 chip as well as the Power10 chips will also continue to have the self-boot engines. Power10 will have more enhancements. What does it do at a high level? It basically does the base initialization of all the Power9 chips. So this is what was done in Power 8 as well. But you can see the bullets that have come up after Power 8 in Power 9. So I think with the first two bullets, like loading host boot also has something called self-boot, and that's only on the master chip. The first two bullets are what more or less the SBE did on a P8 box. But on the P9 box, it actually abstracts the BMC from row-level chip details. So we've come up with a concept of something called chip operations, nicknamed as chip ops. And there are two primary interfaces that can actually talk to the SBE. One is called the FIFO-based interface. So if you look at the legacy one, the legacy hardware access, the BMC had to have all the integrated knowledge of the hardware here, and it had to send SCOM commands, which are basically register reads and writes into the hardware over the FSI bus to do any meaningful hardware initialization or operations. So it clearly was not abstracting the BMC from the details of the POWER9 chip. Starting POWER9, we came up with something called a FIFO interface here. So the BMC actually sends a software protocol command over the FSI. And internally, the SBE is aware of the POWER9 architecture and handles logically which registers to go and what to do directly inside the chip. So that's abstraction here. If you see secure hardware access, it's not just like we can send any commands from the BMC and things will get done. Like you can access memory, main store memory, you can access some registers, but the SBE provides a software-owned blacklist and whitelist of what registers can be accessed and what memory regions can be accessed by the BMC. So it actually is an active, I can say, gatekeeping agent for secure access of the hardware. And the last one is the offload engine for the host software. So there's also an interface that we provide here, which is called the PSU, or the Pervasive Service Interface, Pervasive Service Unit. And entities that are running on the main processor, like the host boot or Opal or Linux, can actually send these chip-op commands over the PSU to the SBE. And that kind of enables some more use cases in the system. We'll come to the details of these use cases later. So I think that was an introduction of the SBE and what scope it had in POWER9. I'll go to the details in the next charts. So this is kind of a hardware block diagram. We don't want to get into details. It's an overloaded chart here. But what I wanted to say is the SBE has, since it's a secure, it's not just a secure access mechanism, it's also the core root of trust for secure boot and trusted boot in POWER9 systems. So if you see the OT-PROM chips right here, these are fuses which are these are CPROMs. I'm talking about the ones here. These are basically one-time programmable chips, and once you blow those fuses, nobody can go and change that code anymore. So that's where an SBE will reset to when it's started first. So it starts executing from the OT-PROM. Control gets shifted to the CPROM, and then it actually starts executing from something called its SRAM. So the previous chart had something called the 96 kilobytes of SRAM, which is a dedicated memory given for the self-boot engine. So its boot process is 3-stage, and we have a chart which kind of delves into the details of that. This is the PPE42 main chip itself, which I talked about. And you can see these boxes. There are multiple boxes around these PEPIs, around the PEPI, which are the bolt-ons. So that's like specific targeted hardware logic, which kind of abstracts the PEPI from what it needs to do. For example, it can execute instructions directly from the OT-PROM. It can execute instructions from the CPROM, as well as from the RAM itself. And all this is like memory mapped or executable because of something called the memory bolt-on, which you can see right here, I guess. So there's a fast I2C one, and there's a memory interface bolt-on here. This is the fast I2C one, which goes for CPROM as well as OT-PROMs. Similarly, you have interrupt bolt-ons. So various interrupts in hardware that the SBE needs to cater to are mapped via the pervasive logic into an interface bolt-on, and so on and so forth. So another key concept here is the SBE itself is a trusted, protected master in the PIB bus, in the PIB architecture. So any SCOMs or hardware access done by the SBE is good. Doesn't matter whether the chip is in secure mode or not. In legacy, all the hardware requests would come over the FSI bus, and they would go either to the FSI SCOM engine or the scan engines, and these engines will be blocked when the chip is in secure mode. So external entities like the BMC can no longer jump on the FSI bus and do anything from these engines. So they have to go into this new interface called the SBE FIFO, and this is one of the external interfaces I was talking about. Similarly, the host has interfaces over the PSU, which is a set of 8 registers. We'll go into the details of this protocol later in this chart. So that's a high-level overview of the SBE's hardware capabilities and what it's built on. The next chart, we'll kind of dig deeper into the FIFO itself. So To give you a context of that, we're talking about this new block that came, which sits in the CFAM domain of the chip. This domain is up and running even in standby voltages. The rest of the chip gets powered on later in the IPL steps. So this is like a blow-up. Any access from the BMC comes from outside and goes over the local bus, and the local bus caters to multiple CFAM engines. So CFAM stands for Common Through Access Macros. They do dedicated functions of actually sending requests from the external entities to the specific elements in the pervasive side of the chip. So you can see there's a new one here called the SBE FIFO, which came into POWER9. And we have specific drivers on the BMC side which target this CFAM device. And using the protocol defined, they actually send commands onto the PIP bus. This is a blow-up of the SBE FIFO device itself. We have one upstream FIFO, which is 8 entries, and a downstream FIFO, which is another 8 entries. So upstream is any commands going from the FSI local bus side, from the service processor, inside the chip, go in via the upstream FIFO. And the hardware maintains, it's a circular buffer. The hardware maintains the rollovers. And any responses coming back from inside the chip, from the SBE, come back over the PIP bus into the downstream FIFO, and they get sent back over the local bus back to the service processor. So this is the intrinsic hardware mechanism. The moment there is an entry here, the SBE would get interrupted saying, hey, you have a new data in your FIFO, and go start processing it. And there's another interrupt provisioned in hardware which says like the command can actually be more than 8 entries, 8 32-bit entries. So the other provisioning is to say I am done with my transfer. Like let's say you have multiples of 8 entries to be transferred. So once your logical command is done, you would get an end of transfer bit set, and that sends another interrupt to the SBE. And it logically starts interrupting the commands it got. And a similar provisioning is on the downstream side. So based on this hardware mechanism, there's a software protocol that has been defined which uses this FIFO. And the command format is very generic. Like we basically have the command class and the command itself, and the length of this command that's expected to come down on the FIFO. And the data could be formatted based on what commands you've been defining in the interface spec. The moment all the data is sent over the command FIFO, you would get an end of transfer, and SBE starts interpreting this command, and the parameters coming in and actually does the execution inside the chip. Similarly, on the response side, we have basically the response. The SBE is, the main challenge on the SBE is it's got really tiny memory. It was 96K RAM, and it had to handle a lot of functions. Like suppose it's streaming out like 1K memory, main store memory. So that won't fit in these 8 bytes, in this 8 entries in the response format. So we start sending the response, and if any hardware function fails, that's when they actually go in and plug in the status of this command. So it could also be success or it could be failure. And then if it's a failure, they end up appending FFDC packages. FFDC is nothing but the first failure data capture, which kind of gives debug information of what's going wrong inside the chip. And the last entry in the response always says, what's my default offset to my status? So this is kind of a flexible response. You never know the length until the command is completed. So, and each FFDC package itself would blow up into something like this. So you have unique codes coming back. You have a primary response code and secondary response code and specific data. So this is like a template protocol, and based on the commands to be supported, it gets architected. So I think there is a spec, a FIFO spec, SBE side FIFO spec, which kind of details each and every command supported. And that's going to be available in the open source pretty shortly. So what are the commands coming in on the FIFO side from the BMC? And before the power bus is initialized, even host boot ends up using some of these. So some of them are just boot and initialization commands. The whole IPL flow could be broken down into steps, and you could actually ask the SBE to go a step at a time. If you see the ones here, the general debug commands, so if something goes bad, you can actually pull out the FFDC from the SBE using a specific chip op. To know what commands this SBE supports, especially when you start upgrading the firmware in the field and start adding new functions, there's a capabilities command which gives you a bit feel of what are the supported operations. Thread control is basically like you can start instructions, stop instructions, reset thread, or you can step instructions in the processor. Typically, it's useful for debug facilities of the host, like GDB and stuff like that. So you have debuggers which want to actually debug host boot, or phyp can make use of this in the lab. There's a host pass-through mechanism command which actually helps health monitoring and stuff in the manufacturing lab to actually facilitate communication between the BMC and the OCC indirectly, but it involves many other subsystems in the firmware. Then there's register access to actually dump out the architected registers inside the Power9 chip. So if something goes bad, you have a check stop or you have a TI kind of condition in the system, you can use this chip up and pull out information to understand the state of what's going wrong. And again, is used in debuggers in general. Secure hardware access. So the basic access is COM registers, serial communication registers, which are 64-bit address registers and data registers, and the rings, which are used when there is no clocks in the system, the very initial steps of the system. So both of these are basic access commands, but you can't simply go and access any register on the chip. So the security team, the security architects, actually define what registers can be read and what registers can't be read, and the read access versus write access for these registers. And SBE does a software-based gatekeeping of this blacklist of registers here. Same holds good for memory access. By default, no memory can be read or written from the main store. But by design, to enable the boot flow or to enable mechanisms like host boot tracing, we want to open up the memory windows for a fixed time in the boot flow and then close them. And again, the opening could be done for read access, write access. So host boot controls what chunks of the memory actually get opened for what pieces of the boot flow. And that's where SBE is again doing the plumbing of maintaining and making sure no random memory can be accessed from the FSI.
What does it mean for the SBE to be in secure mode?
Sorry?
What does it mean for the SBE to be in secure mode?
So there's a hardware facility. There's something called the secure access bit. By default, if the security, there are fuses in the hardware. No. No, there's a separate pervasive bit in the SBE complex. There's a complete security switch OTP kind of chiplet on chip in the pervasive hardware architecture. And it actually samples this fuse on a power on. And based on whether it's blown or not, it says that my chip is in a secure mode or it's not in a secure mode. And if it is in secure mode, all this active gatekeeping would happen. And all the hardware paths, like I showed the FSI, SCOM accesses and the scan accesses, they get blocked automatically, and only the FIFO is open. And SBE does active filtering of the commands that come.
You said it's a fuse, so that means that when you manufacture a system, you want the fuse to be blown?
Yes, by default, all systems would be, like in the lab, we keep some of them open for debug, but I think manufacturing, everything is always secure.
So part of the manufacturing process is blowing the fuse so the
Yes.
SBE doesn't have unreasonable access.
Yes.
And how can something running on the processor tell whether or not the fuse is blown?
I-
The fuse physically resides on the processor. It's not in the system. There's a bypass on the system that we could make.
So you can read it from the processor.
Yes.
That's right. Okay, so I'm switching to the other side, other interface now, because we have really short time. So this is the interface which comes from the host down to the SBE and used for offloading commands to the SBE. So in the pervasive service unit, there's a provision for 8 registers. 4 of them have been used for commands coming from the host down to the SBE, and 4 of them are used for the responses going from the SBE back to the host. So the typical sequence is the host writes its command in these registers, and once it's done writing the command, it would send a doorbell register which interrupts the cell boot engine, and the cell boot engine goes and starts interpreting this command, and based on what it needs to do, it executes stuff and writes back a response here, and then again notifies back the host via the host doorbell, which goes to the PSI host bridge, which kind of interrupts the host saying, I have a response pending. Now, the obvious question is if my commands or responses are greater than these four 64-bit registers, so we actually have a memory mechanism. So in case the command or the response is going to be big, one of these fields actually holds the address of where the rest of the command would reside, or the rest of the response would reside. And the SBE actually will, so the host writes the rest of the command there, writes the command header here and sends an interrupt. SBE reads the overflown command from that piece in memory. So I think that this one is a pretty simple protocol. I won't go through the actual steps right now. And then we have a similar software protocol over the PSU mailbox registers. So we have a command class just like the FIFO, and this is a general template of what the command can contain, and a response with the same thing. We have a sequence ID which needs to match, and there's a FFDC package that was defined on the FIFO side is kept exactly the same on the host side, so that it assists debug, and it's common code across the host and the PMC. So what commands are supported from the host to the SBE side? We have something called a Deadman control loop. So I think in subsequent charts, I'm going to be talking about the boot flow for the POWER9 chip. And at one point on the chip, the host actually goes down, and it needs to reboot all the cores in the system with runtime configuration of the hardware. And to assist that, we have the SBE which is coming in, and that's called the Deadman loop, step 16. We need to initialize, hostboot needs to initialize some of the chip rings. When hostboot wants to go and update the SBE image, it needs to quiesce the SBE so that the SBE itself doesn't go and read the CPROM. So these are some of the initial IPL kind of commands here. Secure access. So I was talking earlier that not all memory is readable by the service processor. So hostboot selectively sets and resets these windows of memory using these chip ops from the host. If you look at this one, this is basically if there's bad failure in the SBE, the FFDC would be written at a known place, and the host code could go and read it up from there. Capabilities and everything else is the same. This is a new thing which was asked by Linux team. So they wanted to offload some specific timers which are above a certain granularity. So we've given them a timer chip op. So Linux can potentially offload some of the timers to the SBE. It's up and running, but I don't think Linux is using it as yet. The last one is the memory preserving IPL. So I think in one of the earlier discussions yesterday, we were talking about the FA dump, the firmware assisted dump for Linux. So that is kind of completely managed by the self-boot engine at runtime. So if there's a terminate immediate or Linux goes down, it can choose to do an MP-IPL. And as part of booting back from this memory preserving IPL, the SBE actually caches the architected states of the registers of the core and threads and pushes it back when the system re-IPLs. So Linux can actually get a state of things when it failed. And on larger systems where you have like 2 sockets, 4 sockets, SBE needs to understand basically how many chips are there on the machine, because when the system is going down, we want to quiesce all the units in the hardware. And when we do that, each SBE kind of monitors the other SBE to make sure that everybody is down, and that's when the re-IPL sequence happens. So hostboot sets this configuration via this interface. I think that's more or less. I think we are in discussions with the Linux team on how to enhance this. So this is going to be a quick run of the firmware architecture on the self-boot engine. So that's the SBE hardware which I kind of touched upon. We have certain functions which are specific based on the PEPI42 architecture. So we have like a targeting mechanism where the different hardware chiplets and their associated properties are captured at like a mini device tree for the SBE. We have a SCOM service, which is just like a load virtual double word and store virtual double word kind of instructions added in this architecture. We have random scan utilities, scan code. So this is like real low-level hardware access based on what you're trying to access on the chip. Typically, since the SBE does hardware initialization during the boot flow, we get a lot of procedures written by the hardware team, which get compiled into the SBE stack. And all of these are basically, they need to follow a certain interface format, which is called the framework API. So the same procedure could actually be recompiled onto hostboot or onto the OCC or any other firmware components that implement this layer. So these procedures actually end up using the standard layer, and the platform code implements this layer. We have a small kernel which is kind of inherited from the OCC 405. The OCC used the SSX kernel, but this is a much more stripped down version of that. It gives very primitive facilities like threads, semaphores, critical sections, timers, and stuff like that. So it also gives the basic tracing support for the system. We have bootloader cores, so when the SBE is asked to boot up, it has 2 levels of booting. We'll touch upon that in one of the subsequent charts. And the control loop is basically the business logic of understanding the protocols from the external interfaces and how you're going to actually interpret the command and the different services required at runtime and IPL time. So that's a high level of the firmware stack. The boot sequence is pretty simple. We have to start booting from the OT-prom code, which is once the fuses are burned, nobody can tamper this code. This is the core root of trust. If the system is in secure mode, as I said earlier, the CPROM also cannot be meddled with by an external entity. Somewhere during the boot flow, hostboot can actually go and choose to update the CPROM in case the SBE has a new firmware coming in the PNOR images. You can see that CPROM is really tiny, it's less than 1K. CPROM is just 256, and then we have error ECCs, so that reduces this capability even more, and the SRAM is just 96. So the moment we reset the SBE, it lands up in the OT-PROM, and that's where it actually sets up the I2C access to the CPROM devices and starts booting from there. It makes sure the magic numbers and the images are good, and then branches to the L1 loader, which is in the CPROM. So CPROM is made up of different sections. It's not exactly ELF, but it's a native IBM format called XIP and likely to change in the future. So we have the loader sections. It branches here, and the L1 loader takes over. It repairs any hardware issues in the RAM itself, and then it would actually copy the L2 loader back to the RAM so that it executes way faster than the CPROM access. Remember, the CPROM goes over I2C, it's slow. Whereas this goes over a parallel PIP bus, it's way faster. Once the L2 loader takes over, it basically has a compressed base image in the CPROM here. We had to compress the image because the amount of function going in was not fitting in memory. So we have used a native compression algorithm here. It's a dictionary-based algorithm which kind of does a histogram of the number of instructions. So the compression is done at build time, and the decompression is done during boot. So the L2 loader boots, copies this image, decompresses it on the fly, and copies it in the RAM, and then just vectors to that address and starts. So that's where the kernel starts booting. And once the kernel boots and initializes the rest of the hardware data structures, that's where you get the application gets control, and the SBE is ready for the control loop business, accepting chip ops over the FIFO or the PSU. Moving to the, whoops, I need to really accelerate here. So moving to the boot flow, so it's apparent like the yellow stars are the external aids that the SBE requires during, during a boot flow, but the blue stars are the ones where the SBE is actually involved and a critical component of the boot flow. So the step one is basically when the SBE itself is booting, and we just showed the boot flow on the previous chart, and then here it's actually ready for going through different steps to initialize the chip. So we initialize the pervasive registers here, we start the clocks. So the steps 1, 2, and 3 are common for all chips in a multi-chip system, but the master chip would execute additionally the step 4 and 5, which is kind of required to load host boot. So the master code and the master core gets initialized in step 4, and then we load the host bootloader image from the CPROM into the L3 cache, and that's where we start running the instructions on the host. So at this point, SBE gives control to the host and is ready to accept chip ops on a master chip. But on a slave chip, it just stops and is ready for chip ops. And then if you see here in the step 8, is when the host boot is running on the master chip, and it can actually trigger the slave SBs, the other chips in the system, to start booting, and they would start from here again. And if the host boot finds a new code update on the PNOR where the SB image is changed, it would trigger an SB update in the step 10 that you see here. Later on, we end up initializing memory and everything, and when the system is ready for business with all the base hardware initialized, it goes to the core initialization. And this is the place where the Deadman timer loop happens in the self-boot engine, where the host boot will actually go to a very low power state. It's called the Winkle mode cycle. And it would start a timer and it expects the SB to maintain a timer, basically. And then the SB will wait for the system to have reached that really low state. And then it reapplies the hardware initialization states when it comes back up in step 16. So it again sends an IPI kind of thing to the host boot, and the host boot wakes up there. So I think that's the contribution of SB in the step. I think I'll skip this chart because we kind of covered this, but in addition to the basic boot steps, we provide secure hardware access, blacklisting, memory access, and the chip ops, which we spoke about. The scan access to host boot via FIFO. So before the power bus is initialized, it goes by the FIFO. SCOM services to host boot for fabric setup, and then the debug services to BMC. Like in the lab, you want to grab the host boot traces or the host boot dump. You can get it from the SB. Runtime services are the timer ones which we have given for Linux. We could end up accessing OCC SRAM from the BMC, but we don't have that use case yet. Host pass-through commands for the hardware monitoring between OCC and BMC. SB asserted kernel dump, which was the FA dump we spoke about. And then debugging a hung machine. I think the NMI request, which was put up on the charts yesterday, so that also is supported by the SB. So there's a chip op which does thread control. And if you do a S reset, it would actually go and get the chip out of a hung mode for Linux. The enhancements coming in the next systems. So basically, we have figured out that there's one FSI bus and there are two masters. The host boot could be trying to talk to the self-boot engine at the same time that the BMC is going to talk. So we have introduced a new SBE FIFO exclusively for the host. And for security reasons, no one else can access this except the host. We're going to have a larger SRAM because a lot of functionality is coming back into the SBE. So we are moving the hardware is getting more and more abstracted from the BMC. So all that is getting sucked into the SB. So we need more space to grab all those functions. We're going to have dumps and checkstop analysis in the SB. It's going to assist that overall firmware function. Improved security. So there were discussions about the SB CPROM being compromised. So to do that, we're going to actually have an immutable measurement CPROM in the future, which improves the secure boot. Debug access of the OpenCAPI memory buffer. I think some of our hardware architects just spoke about that. So we should be able to dump out stuff from this memory buffer if things don't work. And telemetry is something which Todd has asked for, and we're trying to support that on the OCMP as well. So to conclude my talk, the SB hardware firmware co-design has been significantly enriched in POWER9 compared to just booting the host boot in POWER8. And we have major architectural directions. First is hardware abstraction to the BMC. Second was enhanced platform trust and security. So secure and trusted boot and baked-in capabilities for the advanced security features like DRTMs. This is something which we're not using right now, the the dynamic root of trust management. But we have the plumbing in place, so if that need ever comes up, the SB was right there to help with this one. Improved RAS functions. So we talked about the memory preserving boot and the FA dump, the checkstop analysis, hardware dumps, and the S resets for the NMIs. We're also proposing built-in self-test in the future generations for improved RAS. Support host hypervisor offload tasks for improved performance. So we are in discussions with the Linux team on how to leverage this off-chip engine. I mean, off-uncore engine is what they call it because it's not used by the customers. So timers and bulk comms are some use cases which we have right now. And the source is all open. The code is all open source right here. So please feel free to go and make changes or get help on this. This is some of the glossary for the hardware items that I had on the charts. And I think that's all I had. Any questions?
What bus is used to trigger the slave SBE?
What bus? So it's basically goes from the host boot, right? So you just need to go and it's the pervasive interface bus, which is internal to the chip. So it's the slave SBs are sitting on a separate chip itself. So eventually you would get a PIB interrupt into the slave SBs. But when the host sends an interrupt, it would go over the FSI to the other chip. So there's a cascaded FSI between chips. So when host sends an interrupt, host tries to do that, it would go over the FSI onto the PIB bus of that specific chip. So we just need to go to the CFAM there, right? The moment you have a CFAM reset, the SB starts booting. So that maps internally to the PIBMEM and that to the interrupt bolt-on. Yeah?
Are there any PF implications on SBE?
Sorry?
Are there any PF protected execution framework implications on SBE?
Could you elaborate a bit on that?
The secure memory and those kinds of things.
No, I think no. Nothing from the PF front that I know of. Not on the SB.
Well, if you blow that fuse, then you don't have anything.
Yeah, I mean, by default, you choose the system to be secure and you're not going to be able to access the memory. So the security algorithms are like all software defined and which hardware facilities or registers to access or not access. There's a comma separated file available in GitHub. So every SCOM register's base address, which unit it goes to, and whether it should be write accessible or not. And whether it's, I think by default, everything is read accessible. So there's a read blacklist, there's a write blacklist. By default, nothing can be written. So you need a whitelist if you want to write to a register. And that goes through the security architecture discussions to know whether it's that particular hardware register can be accessed or not. So if it's found to be safe, that can be added to that CSV file and the SP just works as it is. Yeah.
When you want to bootstrap the system with a slightly different configuration, for instance, the nest for OpenPOWER, you want to read the transceivers at a different rate, like 20 gigabits per second. I have observed that there's a way you can do it because I have done it in practice, and I see that part of the process is an SBE update. If you can elaborate how this takes place?
Okay, I'm just trying to understand the question. So you're saying it's about the SB update or it's about a different configuration of the...
Transceivers of OpenPOWER at 20 gigabits per second. You have to, in the flash layout of the system, you have to put an attribute with override, they call it. So I see that the system, the host root, at step 10 updates the SBEs.
Yes.
That doesn't understand how it is.
So I think typically in OpenPOWER systems, you have two images. One is the eBMC, and the second one is the PNOR image. So the SB image actually gets packed into the PNOR. And when hostboot boots up, it actually goes and reads the PNOR and tries to compare with what it sees in the CPROM. And if it finds a difference there, that's when it would go for an update.
The update is like it combines itself, changes the procedures.
No, it will actually go and reprogram the CPROM. It would quiesce the SB, reprogram the CPROM, and ask for a reboot. And then on the next reboot, it actually finds them matching, and it's good to go. Any other questions? Thanks. Thank you.